afternoon session of today. The first speaker is Dr. Tetsuya Kobayashi. So he's talking about information geometry of equilibrium and non-equilibrium chemical reaction network. Let's please join me in welcoming Dr. Kobayashi.
Okay, thank you very much for introduction. And first of all, I'd like to thank Hyuno-san and Kim-san for organizing this fantastic workshop. I'm very happy to be here and to have an opportunity to talk about our research work. Okay, in my lab, so we are going to have talk about the relation between information geometry and chemical reaction network. So in my lab, so we are working on understanding biological information processing from theoretical viewpoints. So we have many different projects going on, but so today's talk is related to the question how biological system is constrained by chemical and also physical laws. So the motivation of my work is to understand biological system and how. So actually my background is engineering or applied mathematics, and because of that I often compare the engineered system with the biological system. So most of the engineered system composed of electric circuit, whereas if you look at the cell, it is a collection of the chemical circuit. So therefore it is natural to try to understand the relation between circuit and also biological function. If we look at different types of biological phenomena, we can easily find excellent and also amazing functionality, such as self-replication or adaptive response. Here, the immune cell is tracking a bacteria very adaptively. And also, if we go to the multicellular system, so very complicated chemical information can be sensed more efficiently than any other engineering system we have. And so the question is how we can, and if we look at the specific circuit known to be related to this kind of biological function, what we realize is that we usually have, for example, nonlinear response, perfect adaptation, concentration robustness. Always we find irreversible reaction, suggesting that these are non-equilibrium system, and thereby, so we have to take the dissipation to have this kind of thing. So we want to, the first motivation for us, a very basic motivation is to understand, so this kind of, to understand this kind of relation. So to this end, so we worked in a team.
아까 잘 들리는데. 네. 이제 괜찮을까요? Sounds good.
Okay. So we try. So we worked on this kind of stuff with these members, of very excellent members of my lab. And so what we want to do is to understand and also have unified theory or understanding of chemical reaction and thermodynamics. And to show our more specific motivation, let me introduce a bit more about the history. Actually, the chemical thermodynamics and kinetics has very entangled relation, at least to me. So chemical thermodynamics is very general theory established by Gibbs, and it tells us very generally what did happen eventually in equilibrium thermodynamic system. On the other hand, kinetic theory, for example, law of mass action kinetics, gives us more detailed information how the system behaves. However, this is specific. This is less general than the thermodynamics. Of course, we have historical attempt to bridge between the kinetics and the equilibrium thermodynamics. And the seminal work should be the Schneider equilibrium condition. And for the law of mass action kinetics, if we define the equilibrium state by the detailed balanced condition, then the Schneider condition tells us that the equilibrium constant, capital K here, the log of it should be in the image of the transpose of stoichiometric matrix S. And also later on, so reactant function was found for this equilibrium system, that is the generalized Kobayashi. So this kind of finding was further extended by the monumental work by Ohm and Jackson, and they showed that very similar property can be satisfied, realized even for complex balance system or state, that is non-equilibrium case. Actually, this theory, after this theory, and we have here, so have a very fruitful link, I think, of chemical reaction network theory with the algebraic theory, something that I find about and also here. At the same time, if we look at the history, we have an other attempt to go beyond equilibrium that was initiated by the seminal work of Onsager for the reversible thermodynamics. In this work, he relates the thermodynamic flux and force near equilibrium to obtain this kind of relation. L is the so-called Onsager matrix. It is constant and definite. And also, circuit theories were applied to analyze reversible reaction or non-equilibrium dynamics or linear chemical reaction by Hill and Schneckenberg and other very famous figures in mathematical biology. So we have surveyed different theories and found that this kind of important activity almost has extincted between 80 and 90, unfortunately. But luckily, these theories have revived, I think, independently, for example, in systems biology, in stochastic thermodynamics, as well as in the real algebraic geometry. However, we have many theories in parallel. They are using different techniques, but looking at the same topic, the chemical reaction network. So the question we have is that how are these theories related? So what results are specific to the mass action kinetics and what are not? And why the Kobayashi divergence appear? Is it just coincidence or is there any reason for that? And also we want to have the idea how we can go beyond equilibrium and the law of mass action kinetics, because this is necessary for analyze biological system. In the last 2 years, we have a very big leap in this project, and I want to share the result with you, and also I want to have any kind of feedback from you what we did. So in my talk, I focus only on the reversible chemical reaction network to make it consistent with thermodynamics. So my chemical rate equation looks like this. So here we have S minus, minus S. So this is stoichiometric matrix. My S is hypergraph instance matrix for chemical reaction network. The signs are different. And here we have J plus and J minus. They are reaction fluxes for forward and backward reaction, and J without plus or minus is the total flux. This is defined by the difference of J plus and J minus, like this. And if we assume law of mass action kinetics, J plus looks like this. So it becomes a vector of monomial of X, the concentration of molecules, and kinetic parameters. The key step of our work is to recognize that the chemical rate equation can be related, just related in this way. So this representation link chemical reaction network to generalize gradient, also non-gradient flow. And also we have this kind of diagram that has tight relation to homological algebra and also graph theory. So I'm gonna explain the meaning of this relating step by step in the following slide. So first step is to convert thermodynamic flux to thermodynamic force. So if we assume local detailed balance assumption, we do not need to assume the mass action kinetics, but if we assume local detailed balance assumption, thermodynamic force should be described like this, as a difference of log J plus and log J minus. So this is a thermodynamic flux. That is a difference of J plus and J minus. So their relation is nonlinear. So if we look at the old theory of Onsager, he related force and flux by the linear relation, and this is positive and definite. So near the equilibrium. So this is nonlinear relation. However, if we introduce the spatial function defined like this, and this omega is called a frequency activity defined like this, then we can realize that J is just a Legendre transformation of F by this spatial function. So now, by using Legendre duality, we can have the relation of the J and F like this. So this spatial function is for the chemical reaction is strictly convex, and thereby we can have its Legendre conjugate like this. And these two have very important property. One is non-negativity, and the other is symmetry. Because of this property, if we look at the bilinear pairing of flux and the corresponding force, this is a Legendre transform of J. So this is from thermodynamics is equal to the entropy production rate. So this becomes equal to the sum of two dispersion functions. And from this non-negativity and entropy production rate should be non-negative. This is consistent with second law of thermodynamics. If we assume that so dispersion function is quadratic with positive definite matrix M star like this, then so we can recover nice linear relation between flux and force. And also this bilinear pairing reduced to the squared norm induced by this metric. So therefore, so this is an extension of inner product structure to Legendre dual structure. So the next step is to rewrite the thermodynamic force in this way. So here, this is Kobayashi divergence. So in this case, I assume the law of mass action kinetics. So this is Kobayashi divergence here. This is the variation of it, so of that. And this is the non-equilibrium external force defined like this. X theta is determined by kinetic parameter of the system, and also capital K is the equilibrium constant. Therefore, F is determined by the parameter. So it is easy to verify that. So this kind of relighting hold by just plugging these things. The point is that if we assume that there exists detail balanced at the equilibrium state satisfying the detail balance condition, So in the case of mass action kinetics, that is equal to the Webb-Schneider condition like this. So log capital K should be in the image of S transpose. And this term is already in the image of S transpose. Therefore, if this is in this subspace, then by manipulating an X tilde, we can make F and E equal 0. So this means that in this formulation, the equilibrium dynamics is characterized by the F and E is 0. And in that case, the force becomes the gradient of the Kullback-Leibler divergence. And if F and E is 0, our equation can be called generalized gradient flow. So in order to see the meaning behind it, so let's compare it with the conventional gradient flow on the manifold. So here, so we have divergence and gradient, and so here we have Riemannian metric. And the point is that S is related to the divergence, S transpose is related to the gradient. This is very much consistent with the discrete, the algebraic graph theory or homological algebra. And also here we have the potential function, generating the gradient. If this F is strictly convex and lower bounded, so this can work as Lyapunov function. In our case, Kullback-Leibler divergence is also strictly convex in our case, and also the lower bounded. So major difference is here. So we have Legendre transformation instead of Riemannian metric tensor. Even with this modification, the time derivative of Lyapunov Kullback-Leibler divergence here along this trajectory can be always non-positive. So because we can rewrite this like this, here we have the bilinear pairing of J and the corresponding F. So this was the entropy reduction rate that is non-negative. Therefore, the gradient property is conserved even with this extension, and also by integrating this by time. So we have this kind of balance equation. So this is the difference of Kullback-Leibler divergence at the boundary of the trajectory, and also the integral of, this is the integral of entropy production rate over the trajectory. So this is this relation is also consistent with thermodynamics. So finally, so let's look at the variation of Kullback-Leibler divergence. The Kullback-Leibler divergence is an instance of more general Bregman divergence of a convex function phi. So this convex function is called thermodynamic function. If this phi looks like this, then so Bregman divergence reduced to the Kullback-Leibler divergence. Therefore, this is more general. And also this as a convex function, we can consider its Legendre conjugate as well as a Legendre transformation between X and the Y space. For the case of Kullback-Leibler divergence with this thermodynamic function, the Legendre transformation looks like this. So this looks like the transformation of state to the chemical potential. Actually, so we now have the duality between density and the chemical potential induced by phi, and also the Yuki, one of our members, proved that so this relation is very general by deriving it from very general thermodynamic theory without any kinetic information. Therefore, we can update this Kullback-Leibler divergence with Bregman divergence. And also another important observation is that this variation can be described like this. F is the chemical potential corresponding X, and also Y tilde is the chemical potential corresponding to the X tilde. So this is a summary of our rewriting. So chemical rate equation enable us to calculate the time derivative of x dot based on the information of current state. So we want to calculate this starting from the current state. So by calculating the variation of Kullback-Leibler divergence or more generally Bregman divergence, we have a member of the cotangent space here that is obtained by the difference of chemical potential of the corresponding state and also some contribution from of parameter here. So this is related to the equilibrium dynamics. And this vector is mapped by S transpose. This is gradient equation to the thermodynamic force with additional contribution from external force, external non-equilibrium force. And this force is now transformed by the Legendre transformation to the flux. So by this, and at the end, by applying S, this is a continuity equation, we get x dot from starting this state. So this is a structure. So it is easy to notice that here, the dual spaces are related to the chain and the cochain complexes on the hypergraph, defined hypergraph. However, major difference is that we have Legendre duality between here and also the base kind of base space. So usually, we have inner product structure here, but now we have nonlinear Legendre transformation. We have to handle it somehow. So now the information geometry plays a role to address this problem. So information geometry is, in a narrow sense, the geometry of statistical models, basically initiated by the seminal work by Chensov in Russia and also Amari in Japan in 70s. After that, so this theory has been intensively investigated very locally in Japan. So he was the leading person in this work, and actually my lab is the direct descendant of my lab. His lab, actually, my supervisor inherited his lab, and so I inherited my supervisor's lab. So I'm direct descendant. But anyway, and in the development in the last almost half a decade, so we realized that information geometry has many aspects. So one of them is the geometry of the Legendre dual spaces that I'm gonna use. The important ingredient of it is the so-called dually flat space and dual foliation. So this can be regarded as a generalization of inner product dual space and also oblique coordinate obtained by the complementary subspaces. One is defined in the primal space, the other, later on, is defined in the dual space. If we map this complementary subspace here by this metric, then we get oblique coordinate. So even if we replace this linear mapping with Legendre transformation, so we can still enjoy very nice property that this inner product dual space has. So if we map this lit complementary subspace to blue one, so then we can have these curved manifold. Even with that, so this structure inherits something from here. So this form a kind of nonlinear coordinate that is called sometimes called dual foliation. The point is that intersection of the complementary subspace is still unique, thanks to this property, and also we can use generalized Pythagorean theorem and also the projection in this space. So in our problem, so we have two pairs of complementary subspaces. One is here and the other is here, related to the stoichiometric matrix. And from each of them, so from former one, so we get the dual foliation and dually flat structure on the density and potential space. From the other, we have another dually flat structure from on the flux and the force space. So let's look at what do they mean. So for the dual flux structure on the x and y space, potential and density space, so the subspace we have in x is related to the stoichiometric compatibility class or stoichiometric polyhedron like this. So that position is determined by the initial state of the system. Its complementary linear space in the potential space is a set of equilibrium state for a given kinetic parameter in the case of mass action system. So we can map this by Legendre transformation to the density space. Now we have curved manifold. So in the case, if the kinetics is mass action, so this is nothing but the toric variety worked on the mass action chemical reaction system. So the equilibrium state is determined by the initial state and also the parameter of the system. That is unique because the intersection of these are unique thanks to the dual flux structure. So this is a generalization of the so-called Biot's theorem. For the dual flux structure on the flux and force space, we can generalize the Helmholtz-Hodge decomposition. So in this case, we have two decompositions. One is primal and the other is dual. And so here, this J is decomposed into two, and JCF is related. I'm sorry, so this is not. So maybe this should be K. So this is related to the curl free force, and the remaining part corresponding to the divergence free part. So for the dual decomposition, so this part corresponds as the corresponding flux of this force is divergence free, and the remaining part is the curl free. So because Legendre transformation is generally nonlinear, these two are different. If it is linear, then these two becomes the same. So for the primal decomposition, so it is related to the equilibrium kind of decomposition, because if our flux J is equal to only the curl-free term, then so we can obtain that F and E equals 0, meaning that system is equilibrium. Therefore, this is a decomposition of generally nonlinear flux into the equilibrium part and also kind of non-equilibrium part. So if we look at the dual decomposition, so here if we have the so F is equal to FDF. This is its corresponding flux is divergence free. So in this case, X dot becomes 0 because the flux is in the kernel of S. So therefore, so this decomposition characterizes the steady state of the kind of flux. So that decomposed flux into the part that generates current state in a steady state, and also the remaining state. So we have this kind of interpretation for this decomposition. And finally, by using these two decompositions, so we have Legendre dual structure on the force and flux space. We can obtain the induced dual structure in the tangent and cotangent space, as well as cycle space. By using primal decomposition, we can have this induced structure, and this structure is generalization, a kind of generalization of so-called Otto calculus. That is the formal Riemannian geometric structure induced by Wasserstein geometry. That is very intensively used for analyzing the diffusion processes in the last 10 and 20 years. So the other parts, so we have the duality in the cycle space. So this is a generalization of network thermodynamics for the transient state and also trajectory. So usual network thermodynamics did cycle space characterization of steady state at only real steady state, but we can do it by do it even for transient or for the trajectory. So finally, so this is a summary of my talk. So our tentative answer to our question is that chemical reaction network is a generalized flow, gradient or non-gradient flow. Redundant duality are fundamental not only for thermodynamics but for kinetics. And redundant dual space plus the network structure is something like the generalized version of discrete differential form. We are calling it the dual flat form. And we think that so our theory can provide a path to go beyond, of course, go beyond equilibrium, as well as law of mass action kinetics. So because of the limitation of time, I cannot touch on the relation of complex balance state to our theory. So actually, so we can characterize complex balanced state by using another type of projection called generalized Hilbert orthogonality by using the affine central manifold in information geometry. And also we have extended this kind of approach to growing chemical reaction system, the chemical reaction network with changing volume, change in volume in relation with the reaction inside it. So we are very much interested in how we can explore this theory further, and also we are interested in the link to the algebraic approach, because so we are not so much using it here at this moment, and also we are trying to apply our very abstract theory to more specific biological problem. Okay, finally I'd like I thank again my collaborator and the funding agency. Thank you very much for your attention.
Thank you. And any question?
Thank you very much. Very interesting. I cannot follow enough. So yeah, this may be a stupid question, but could you tell me how your theory can be used to understand the non-steady dynamics?
Non-steady or non-equilibrium dynamics?
Non-equilibrium. It's different.
Okay, yeah. So what we are thinking is that by using this kind of decomposition or here, so this J and F can be general one, that can be non-equilibrium. So by using this technique, we can dissect the contribution from equilibrium and also non-equilibrium. So this is what we want to do, what we can do by directly using this. And also maybe we can do a bit more by exploring this kind of structure, I think. But I'm sorry, I do not have very specific answer to your question yet.
Thank you very much.
Actually, if we look at a trajectory of chemical reaction system, so that may be realized by non-equilibrium chemical reaction, but we can maybe mimic it by equilibrium dynamics, and remaining part may be necessary, or I don't know, but so will contribute to the dissipation, because that trajectory can be realized by equilibrium dynamics. So yeah. Then actually in physics, so some people are very much working how we can dissect the equilibrium and also non-equilibrium contribution.
I have also a question. So for here.
Oh yeah, yeah. Sorry.
So for equilibrium dynamics, your system can be written as x prime equal to s times j plus minus j minus, right?
Yeah, something like that. Yeah.
If you assume the system is a non-equilibrium, then
Mhm.
you cannot anymore write the right hand side as j plus minus j minus, right?
J plus.
So yeah, because every reaction is not anymore reversible.
Oh,
For non-equilibrium, is that one the key reason why if you assume non-equilibrium dynamics, all the analysis may not work?
um, so what we are thinking is that of course, if we look at the model
Yeah.
or from say systems biology, so some reaction network only has some reaction only have forward reaction. So, but that
Yeah.
is from physical viewpoint, that is a kind of extreme situation, or it is a kind of approximation. The reverse reaction should exist if this is the physically relevant. But it is very small, then so people ignore it. But yeah, if at the limit, of course, the entropy production diverges. I think in that case because we can only have the one-way flux. So we can understand that kind of thing more quantitatively if we start from equilibrium state and then changes the kind of non-equilibrium aspect, or if by modulating the parameter, then so we can make the system more non-equilibrium. And then so we can see that and what happened about the biological functionality or other behavior if we do this kind of thing.
Then what's the benefit of thinking the dual space instead of just concentration X?
To me, everything becomes much clearer. So sometimes, yes, the dual space, so we can present everything without dual space. But if we look at the thermodynamics, the dual space is very fundamental. Sometimes chemists use the chemical potential rather than concentration to talk. So, and also this is very much maybe related to the vector calculus and also electromagnetics and something like that. And yeah.
Thank you. Okay, any other questions? Okay, otherwise we can wrap up the first talk. And let's thank the speaker again.